So today we're going to take a look at section 3.1, which is called Extrema on an interval. And this is one application of derivatives. Okay? So to start with, we're going to let f be defined on an interval containing an interval I containing c. And we're going to define what we mean by a maximum and a minimum in some concrete terms. F of c is the minimum of f on I when f of c is smaller than or equal to all of the values, all the y values in the interval. And f of c is a maximum of f on I when f of c is greater than or equal to all of the y values in the interval. I'll draw you a picture in a second. The maximum and minimum values on an interval are the extreme values, or extrema, of the function on the interval. You will also hear them called the absolute maximum, absolute minimum, or global maximum and global minimum. All interchangeable terms in different resources. So image-wise, if you have a graph that looks something like this, this would be my maximum. And again, the definition says it's bigger than all the y values. Yep, it is, right? It's the highest the y value goes. If you were looking for the range, this would be the biggest range value. And then your minimum happens to be right here. All right, so this is my min, this is my max. Because it's the smallest y value. Again, so it's the range values. If I were writing down what is the range for this function, the way I describe it when I teach this in college algebra for range is I talk about climbing up the y-axis like it's a ladder. So if I climb up the y-axis like it's the ladder, the smallest y value that I see is the first value of the range. That's my minimum. And then when I stop seeing y values as I continue up, that would be the upper end, the maximum of my range, and that would be my maximum of my function. Now you'll notice those 2 points are different kinds of points. One of them is an endpoint, right? The other one is not. So sometimes maximum minimums occur on the endpoints or the extrema of our interval, because this is being done on an interval, right? This is the interval I. So in our interval here, we're saying that my interval is basically between these x values. I've truncated or I've paused and I've only considered part of my graph. And then the minimum is actually occurring at this sort of valley point, okay? So these valleys and the peaks, we'll get to them later too, are other places where I might have maximums and minimums. Now the extreme value theorem says that I've always got one. If f is continuous on a closed interval, then f has to have a maximum and a minimum on the interval. So it's never does not exist. They will exist. And they will exist at either the end points or at these peaks or valley points. Now, relative or local extrema are the peak and valley points. So if there's an open interval containing c, on which f of c is a maximum or minimum value, then you can say that f has a relative maximum or a relative minimum at c f of c. And it works pretty well to think of it kind of like this. If all of us in this room were to stand up, there would be someone in this room who's the shortest and someone in this room who's the tallest. Agreed? I mean, there may be more than one person who's, identically the same height at the shortest or the tallest end of that spectrum, but there would be at least one person who is the tallest and at least one person who's the shortest. But there's no guarantee, Alyssa?
What if it's a straight line?
It still has one, right?
I mean, like, horizontal.
Then it's the same thing. You just have the same maximum and minimum. They're equal to one another. We're not going to be dealing with functions that are going to be straight lines because that's not very interesting to look at from a calculus standpoint, but technically it would still be the same answer. The endpoints, or even in this one, anywhere in between, would have the same maximum and minimum value on this one. Yeah. However, if we stood everybody up and I said, I don't even know who's the shortest, but let's say that, do you think you're the shortest, Alyssa?
Yeah.
Alyssa. We'll say Alyssa is shortest. Okay. So Alyssa is the shortest. That does not mean that she's the shortest person on campus or in the world or something like that, right? On a big grand scheme, in a bigger grouping, she may not be the shortest person. Agreed? So she's not a global minimum or an absolute minimum. It's just relative to our group of people that we're considering. The same thing for the tallest person. We got some tall young men in this classroom, so I have no idea. I'm looking at some of you. I'm like, I don't know which one of you is the tallest. To go tall people here. So we have the same issue here, is that there's these differences between talking about if it's relative or if it's extreme. When we moved to Ohio, my husband was a youth pastor, and we had some really tall youth at the time. And I think I was the shortest person anytime we got together with all those teenagers. And I don't really think I'm super short. I mean, 5'4" is not super short, but it was pretty short compared to all those people. In a relative sense, I was very short among those group of people. So as we're taking a look at this picture, if I have an image sort of like this would be an example of a relative minimum, and this would be an example of a relative maximum. Now, these locations where I see these peaks and these valleys, they actually have a more broad name that we can use. We can call them all critical numbers. So critical numbers are defined like this. So we're going to have f, and it's going to be defined at a value c. If f prime of c is equal to 0, or if f prime of c is not differentiable at c, then c is a critical number of f. So this f prime of c equals 0 is what happens when I have a nice smooth curve when I have a peak or a valley. This would be an example of where f prime of c is 0. This would be at the x value of c. Okay? Nice smooth peak or valley. But it doesn't have to be nice and smooth. It can be a sharp turn as well, and it also be a critical value. So this would be an example where f prime of c does not exist. Still happening. I still have this at c, but I've got the sharp turn. But it's still a peak or valley. And you can look at both of those and say, yeah, those are both, based on the portion of the graph I've drawn, relative maximums, right? Now, there are some places where we have some hills, right? And some of them are lower and higher than others. So just because we have a graph that has these doesn't mean that they're all relative maxes and mins. So, or at least the absolute maximums and mins. So this would be, and this would be, these would all be maximums, but you can tell that the maximums are not at the same height, right? They're not. But in a local area around them, they are the highest value. So they both are considered relative maximums, even though they're at different y value heights. If f has a relative minimum or maximum value, then c is a critical number. So this is telling you that if you have a critical point, it's going to give you a potential maximum or minimum. But if you have a maximum or minimum, it is in fact going to be a critical point. The reason that they're trying to distinguish that is because there's one case I haven't drawn. It's something that looks like this. If this were drawn well, I'm not guaranteeing that it is. That point that I've plotted there, if I drew a tangent line, it'd look very horizontal, look very flat. Well, the slope of horizontal lines is 0. So this is f prime of c equal to 0. It's flat there, or at least it is if I draw it well. But it's not a maximum or minimum value, right? I don't see a peak or a valley there. A flattening out spot, but it's not a peak or a valley. So it works in one direction, but it doesn't work in the other. I don't always get peaks and valleys from all places where I have derivatives of 0. I just have potential peaks and valleys. So there are some conditions and some guidelines for finding these peaks and valleys, these extrema points on closed intervals. So if we're going to try and find the extreme value for a function on a closed interval AB, the first thing we're going to do is to find the critical numbers of f in AB. So what does that mean? Well, it means we're going to take the derivative and we're going to set it equal to 0 or equal to does not exist. You'll see what I mean when I do that later, okay? And we solve. That will find us critical numbers, because that's what critical numbers are. They're places where the derivative is 0 or doesn't exist. So that's step 1. Step 2 is to actually take those values then and evaluate them. So if I find out that this has a derivative of 0 at x equals 7, then I plug 7 back into the original function and I figure out what is the y value at 7. So this is to evaluate f of c. Plug it in, see what happens. Now, if you'll remember the very first picture I drew over here, I talked about the fact that yes, peaks and valleys give me maximums and minimums, but endpoints can too. So step 3 says, okay, you got to check out the endpoints then as well. What's going on the endpoints? So you have to find f of a and f of b. What are the y values at the endpoints? And then you look at all the y values that you've found on steps 2 and steps 3. The biggest y value is the maximum. The smallest y value is the minimum. The most common thing that happens when people are finding critical or finding global extrema like this is they do half of this problem. They either do only the setting the derivative equal to 0 solving and using those values, or they do only the endpoints, and they forget to do the other half of the problem. So they're not considering all the values at the same time. That is the biggest mistake. And it's probably 50-50 on which one people do more than the other one. Okay? So let's do some examples and you can see how it works. Not all these directions say to find critical or to find global extrema. So we're going to take it step by step as the directions do say. All right, so example number 1 just wants us to find critical numbers. Okay? So anytime you see critical numbers, what it's asking you for is for the derivative to equal 0 or does not exist. Okay, that's what it's asking you for. Find a critical value. It means find the derivative, set it equal to 0, and it will be either a value or set it equal to 0 or does not exist, and you will get values. Now, you'll all be very pleased to know that once we get into chapter 3, all your derivatives become much easier to work with. We're not doing we're not doing near as difficult of questions in terms of find the derivative as you did before. So, breath of fresh air in terms of that. What's the derivative of x cubed? 3x squared. And what's the derivative of negative 3x squared? Negative 6x. And we all said, oh, right? Yeah, we do. Now, we can set this equal to 0. It's great. There is no does not exist on this. So let me talk about when you have the does not exist. You have does not exist when you have denominators. That's when you have it. So if you have a denominator, you're going to have to figure out where the denominator is equal to 0, because you can't use that as a value, right? I don't have a denominator here, so I don't have any does not exist. So I'm just going to set this equal to 0. So now you're back into algebra, like the college algebra stuff, right? Like the intermediate algebra stuff, like the algebra 1, algebra 2 from high school. You're factoring, you're solving, you're moving things around depending on what the question looks like. On this one, you're factoring. So what do each of these have in common? 3x. So we're going to factor the 3x out, which gives me x minus 2, like so. Then you're going to set each part equal to 0. So 3x equals 0 means x is 0, and x minus 2 equals 0 means x is 2. And that's all this question asked you for, the critical numbers, the x value locations where I have derivatives of 0. Now, what you would expect, right, you know what this graph roughly looks like. It's a cubic graph, right? Cubic graphs look something like this, or maybe flipped around like this. That was terrible, like that. You would expect that there's a peak and a valley somewhere in between here, right? One of these, x equals 0, x equals 2, is probably a peak. One of them is probably a valley. So could you confirm it with a calculator and a graph? Yeah, you could get a good idea if you have the right plan. If you just graphed this and see, do I have a peak or a valley there? and you'll be good to go, and you will see those pieces, okay? All right, we're going to expand our directions now to actually find absolute extrema. So we'll have that first step we just did on the other problem, finding where the derivative equals 0. Like, that's going to work. We're going to do that part of it. But we're going to have more to do after we find those critical numbers. So I'm going to write out that we have each of these steps. This is sort of step 1. You don't have to write out steps when you're doing all of your work, but I don't want you to forget them either. Like I told you, half of the people are going to forget half of this problem, and that's not cool. So I want to make sure we're careful on that. So we're going to find the derivative equal to 0. That's my first step. So what in the world is my derivative for this function? Negative x squared plus 3x minus 5. Fabulous. Negative 2x plus 3. This one's actually even easier than the last one, right? Because the last one I ended up with a quadratic and I had to factor. This one's just a line. And so if I set it equal to 0, there's no factoring. There's just direct solving. So I have negative 2x is equal to negative 3. X is 3/2. Is everybody good with that? Okay, that's step 1. That's the finding the critical numbers step. Step 2 means evaluating at that point. So I'm going to find f of 3/2. Not f prime. I know f prime of 3/2 is 0, but f of 3/2. The original function. So I have negative, I have 3/2 squared plus 3 times 3/2, and then minus 5. You can do derivative, you can do decimals, you can do fractions, I don't really care. Grab a calculator if you want to or need to. I need to know what this y value is. You can do it by hand if you want to, I don't care. Somebody, when you get to it, find me the y value here. What was it?
Negative 11.
Yeah. Negative 11 over 4. Okay, is everybody good with that? Okay, we actually have encountered a problem that I haven't identified yet. We'll come back to the problem in a moment, but we're going to keep going through our steps, and then I'll come back to that problem, okay? Step number 3 means to test the endpoints. So I have to test the endpoints of the interval that I was given. It says the closed interval is from negative 2 to 1. So I need to test f of negative 2 and f of 1. So I'm going to plug in negative 2 squared plus 3 times negative 2 minus 5. And I'm going to do 1 squared plus 3 times 1 minus 5. Okay, so what is f of negative 2? I don't have negative 7, but I might have an error.
There should be a negative on the other side.
Oh, I left my negative off? Or there... Oh, I did. Right here, huh? Is that what I'm missing? That's my fault. I'm so sorry. That's 1 squared with a negative on the outside. Negative 15 is what I have written down. Good. And then how about the second one? Negative 3. Okay, are you ready for me to tell you what my error is? Not error, but problem from the first part. This particular location for x, 3/2, is not on my interval. It's not between negative 2 and 1. Are you with me? And I'm supposed to be looking at only the interval from negative 2 to 1. So right here, this piece, it's actually irrelevant. And I put this in here on purpose because that happens sometimes. Sometimes you'll get 2 answers, and one's on the interval and one's not. This one only had 1 answer. It's not on the interval. So it's almost like you had an image. In fact, this is an x squared, and it's opening downward. And what they did is that they restricted the interval to only include this part of it. Okay, please don't tell me I drew my graph wrong. I'm just giving you a sketch idea. The problem is that the relative extreme point here, the peak, right there, it isn't on the red part of the graph. It isn't between the lower value and the higher value that I am actually supposed to be considering. So it's actually not an absolute extreme on this closed interval. So this one would be my minimum, and this one would be my maximum. And I'll let you do this one of two ways, and let me show you what the two ways are in terms of writing what your answer can be. So one option, smaller. So step 4 is my evaluation over here of what's going on. So one option is to write down that my maximum is at, I have a maximum of -3 at x equal 1, and a minimum of -15 at x equals -2, right? So that's one way to write the answer. Perfectly acceptable. It's the maximum value and where it occurs. Or, if you wish, you can say that you have a maximum at 1, -3, and you have a minimum at -2, -15. Okay, so one of them is more verbal description, and the other one is more of an algebraic, like point valued description. WebAssign may want you to do one or the other. As far as I'm concerned, you can do either one on any work that you hand in to me. They're equal ways of writing the same thing. Is that good? Okay. We have two more with the same directions. Okay. Find the absolute extrema on the function. Now we have one that's not a polynomial. It's a rational function, right? It is kind of worth noting that the interval from 3 to 5 doesn't include the asymptote. Where is this going to have a vertical asymptote? Yeah, at t equal to 2, right? So the 2 is not on that interval. So it is going to be continuous. That's actually really important because all of my absolute extreme theorems at the beginning and definitions and everything hinged on the fact that my function was continuous. And if I was actually including the asymptote spot, it wouldn't be continuous. So that matters. As far as working through the problem, we're going to go through the same steps. The first thing we need to find is where the derivative is equal to 0. So I need to find the derivative. This is a quotient, right? So I have my denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. And technically, I should also be finding where the derivative does not exist. We've already talked about that. That happens at t equals 2, and it's okay, though, because this is not on the interval 3, 5. So I don't get any new information out of it from there. So I really only have the first piece. So this is going to be t minus 2 minus t over t minus 2 squared. So I have negative 2 over t minus 2 squared. And I'm supposed to find out where this is equal to 0. So, where is it equal to 0? It's not. It's never 0. A fraction can only be 0 if the numerator is 0. Can this numerator ever be 0? No, because there's no variable left in it, right? This numerator is negative 2. It's constant. So this does not equal 0. What does it mean? Well, it means that there's no critical points. It means that on the portion of the graph I'm looking at, I have something maybe like that. There's no peaks and valleys. That could happen, right? Nothing wrong with that. It's totally a possibility. So step 1 and step 2 don't yield anything for me to consider. So I'm down to step 3. So this is 1 and 2. So step 3 tests the endpoints. So I find h of 3 and h of 5. So I have 3 over 3 minus 2, which is what? 3. And then I have 5 over 5 minus 2, which is 5 over 3. Okay, that's step 3. Step 4 is to actually consider, well, truly, it's considering all of this, but I didn't get anything from the first pieces. And I need to figure out which one's the maximum and which one's the minimum. So 3 and 5/3, which one's the bigger of the two values? 3. So this one's my max, and this one's my min. So again, I'm going to write it last time for like this. This is going to say it's a maximum of 3 at x equal 3, and a minimum of 5/3 at x equal 5. Or you can say it's a maximum at 3, 3, and there's a minimum at 5, 5/3. Okay, so you don't need both of those statements, but either of those is acceptable. No lesson would be complete without a trig problem, right? I see some cringing of faces. All right, let's give it a try. Find the absolute extrema of the function on the closed interval. G of x is 3 cosine of x. So hopefully you have in your mind what a general cosine curve looks like, right? It oscillates up and down, waves, right? Nice, smooth, continuous, it's all lovely. This interval is actually your basic unit circle interval from 0 to 2 pi as well. Okay, so same process. We set the derivative equal to 0 and solve. So what in the world is the derivative of 3 cosine of x? Fantastic, negative 3 sine of x. Then we're going to set this equal to 0, and we're going to have to remember something about a unit circle. In particular, we're only on the interval from 0 to 2 pi, so that's actually very nice. I only need the unit circle interval itself. So where on the unit circle is your sine value equal to 0? Let me actually make one comment. I can divide by negative 3. The negative 3 doesn't change anything on this problem, so really I'm finding where the sine of x is equal to 0. That's the jump I made. I didn't write. I'm sorry. So where is the sine of x equal to 0? At the angle measure of 0 and 2 pi. Anywhere else? At pi. Yeah, so it's every half of my unit circle. And if you remember from a unit circle perspective, I'll just mention it this time only because it's a really nice quick one, is that on your unit circle, sine values are the y values, and you notice right here you have a y value of 0, so that's at angle 0. And all the way over here, your y value is again at 0, the sine value is 0, so you have that at pi. So you have three points. Interestingly enough, 2 of the 3 points are actually our endpoints anyway, aren't they? They actually are. So as I take a look at setting each of these things equal to 0, and I find g of 0, g of pi, and g of 2 pi, I kind of get the endpoints for free because they happen to be places where the derivative is equal to 0 anyway. So I don't have any new information from the endpoints. I simply have 3 points to consider. So I need to find 3 cosine of 0, 3 cosine of pi, and 3 cosine of 2 pi. So what is 3 cosine of 0?
Or 3.
Okay, it's 1 and then times my 3, so I have 3, right? The 3 in front. Okay, what is the cosine of pi? That's negative 1 times my 3 is negative 3. Again, if you're struggling with unit circle stuff, brush up on it. Come see me on it, we'll chat. And then how about the cosine of 2 pi? That's 1 again times my 3, so it's 3. So what is my max? 3. And I got it here twice, right? You can have two maximums on an interval. And I have the minimum in between. So I have a max. I'll do this in an interval or in a ordered pair notation. I have a max at 0, 3 and 2 pi 3. And I have a minimum at pi negative 3. Or of course you can write it the way I wrote it on the other ones too. Any questions on those? Okay.